Hello guys, today I'm going to propose a solution of the exercise 4 ter of the chapter matrix calculation, and we're going to prove that all square matrix can be expressed in a unique way as the sum of a symmetric matrix and a skew symmetric matrix. So we are going to prove that all square matrix can be expressed in a unique way at the sum of a symmetric matrix and a skew symmetric matrix. In this exercise I put S sub n of k is equal to the set of the symmetric matrix of m n sub n of k, and I put A sub n of k the set of the skew symmetric matrix of m sub n of k. And we are going to do that with two steps. In the first step we are going to prove that a square matrix can be expressed as the sum of a symmetric matrix and a skew symmetric matrix, and in a second step we are going to prove that there is a unique way to do that. First, let A be a square matrix which size is equal to n, and let's prove that there exist B and C that belong to the Cartesian product of S sub n k, S sub n of k and A sub n of k, such that A is equal to B plus C. That is to say, we are going to express A as the sum of a symmetric matrix and a skew symmetric matrix. And we have got to find B and C, so the first step is to look for B and C. And to do that we are going to do first an analysis and secondly a synthesis. First part, analysis, looking for B and C. We're going to assume that we have already found B and C, and then we're going to find their expression. Let's assume that we have found B and C such that B is a symmetric matrix, so B belongs to S sub n of k. C is a skew symmetric matrix, that is to say C belongs to A sub n of k, and B plus C is equal to A. And we're going to find the expression of B and C. As A is equal to B plus C, we have got one equation, and we are going to write another equation to find B and C. So we can calculate the transpose matrix of A. Transpose matrix of A is the transpose of B plus C, so is equal to transpose of B plus transpose of C. And as B belongs to S sub n of k, B is a symmetric matrix, so transpose of B is equal to B, transpose of C is equal to minus C, because C is a skew symmetric matrix. So we get transpose of A is equal to B minus C. So now we've got two equations, this one and this one. And we have got to solve this system of two equations. We solve the system A is equal to B plus C, transpose of A is equal to B minus C. To solve this system of two equations, we notice that if we sum the two equations, we get A plus transpose of A is equal to 2B. So B is equal to 1 over 2 multiplied by A plus transpose of A. And if we subtract the two equations 1 and 2, we are going to get 2C is equal to A minus transpose of A, so C is equal to 1 over 2 multiplied by A minus transpose of A. And then we have got the expression of B and C. This is the end of the first part, analysis, and then second part, synthesis. I put B is equal to 1 over 2 A plus transpose of A, and C is equal to 1 over 2 A minus transpose of A. And then I'm going to check that B and C hold the wished properties. That is to say, B is a symmetric matrix, C is a skew symmetric matrix, and A is equal to B plus C. Let's go. B is a symmetric matrix. B belongs to S sub n of k, because if we calculate transpose of B is equal to transpose of 1 over 2 A plus transpose of A is equal to 1 over 2 multiplied by transpose of A plus transpose of A is equal to 1 over 2 transpose of A plus transpose of A is equal to 1 over 2 A plus transpose of A plus A, and is equal to B. We do the same with C. C belongs to A sub n of k, because we calculate the transpose of C is equal to transpose of 1 over 2 A minus transpose of A is equal to 1 over 2 multiplied by transpose of A minus transpose of A is equal to 1 over 2 transpose of A minus transpose of A is equal to 1 over 2 transpose of A minus A is equal to minus C. And at last, A is equal to B plus C, because B plus C is equal to 1 over 2 A plus transpose of A plus 1 over 2 A minus transpose of A is equal to A. So we have proved that there exist B and C where B is a symmetric matrix and C is a skew symmetric matrix, such that A is equal to B plus C. Secondly, we are going to prove that there is a unique way to express a square matrix A as the sum of a symmetric matrix and a skew symmetric matrix. Let's prove that there is a unique way to express a square matrix A of M sub n of k as the sum of a symmetric matrix and a skew symmetric matrix. Let A be a square matrix, and we have seen that in the first part we have seen that we can express A as the sum of B and C, where B is a symmetric matrix and C is a skew symmetric matrix. And we have seen in the analysis that if B and C exist, necessarily B is equal to 1 over 2 A plus transpose of A, and C is equal to 1 over 2 A minus transpose of A. So immediately there is a unique way to express A as the wished sum. We have seen in the analysis that if A can be expressed as the sum of B, a symmetric matrix, and C, a skew symmetric matrix, necessarily B is equal to 1 over 2 A plus transpose of A, C is equal to 1 over 2 A minus transpose of A. Hence, there is a unique way to express A at the sum of a symmetric matrix and a skew symmetric matrix. Bye bye.